Good afternoon, everyone. Welcome to today's CLSP seminar. I'm going to introduce Kate Sanders, who I think many of you know, current fourth year PhD student in the department working with Ben Van Jeremy, and Reno Kriz, who's over at the COE as one of our research scientists. They're one of the research faculty. And today they're going to be talking about Scale 2024, which is one of these summer programs similar to JSALT that we run at Hopkins every year, and some of the cool stuff that they've done on multimodal information retrieval. So with that, welcome Reno and Kate.
Thanks, Captain.
Hi, everyone. So as Kenton already nicely introduced, we're going to be talking about Scale 2024. We've divided the talk into three main portions. First, I'm going to be going over the general problem that we tackled during Scale and the motivation behind it. And then Reno is going to go over the details of creating the benchmark that we used for the workshop and then the results of hacking away on this benchmark for 10 weeks. So starting off with the motivation, the general topic that we were considering for the workshop is video event retrieval, which can essentially be loosely described in a few words as the problem of given a text query and a corpus of videos, the goal is to return all relevant videos from that corpus that pertain to the event that is described within this natural language text query. So for an example, say that we pass in the text query the Notre Dame fire. Ideally, given a corpus of videos, the output of a retrieval model would look something like this. And so, as you are probably vaguely aware of, even if you're not in the field of information retrieval, there are decades, if not centuries, of work that have been done on the field of information retrieval. You can go back to the Library of Congress. There was initial work being done in the space then. And so in this time, very efficient data structures and algorithms have been developed, specifically in the context of text documents and retrieval over corpuses of these text documents. And so you may be wondering, what's different about this task? Haven't we already seen this sort of research being applied to spaces like YouTube, for example? Well, if you take a look at YouTube, you'll notice that there's actually a ton of text-based metadata that is associated with every video on the platform. You have the title of the video, you have the number of views, you have the description associated with it uploaded by the user. You additionally have all of the information that YouTube has about you. It has your history, your subscriptions, the videos that you have uploaded. And so with all of this information, there's even more if you look at individual videos. You have, as I said, the title and description, but you also have hashtags, you have the like count, the indicators as to whether this is even a good video that anybody wants to retrieve. And so really, YouTube isn't actually doing a whole lot of work looking at the actual video content itself. It is using all of this text-based metadata to leverage this vast amount of work that's been done in the space of information retrieval on text documents in order to retrieve videos for you when you type in a query. And so we're departing a little bit from this paradigm in that we actually want to primarily be considering the video content itself. What if you have a corpus of videos where there isn't this massive amount of text metadata associated with it? And then furthermore, in addition to the challenges that are introduced by not considering all of this helpful text metadata, you have the problem of the fact that we're specifically looking at retrieving based on events as opposed to just general text semantics. So given the query of the Notre Dame fire, that's specifically considering an event. If you look more towards traditional video retrieval benchmarks, the query would probably be reduced to something more like just Notre Dame, in which case you'd end up with videos like this covering the football team as opposed to the cathedral, which we actually care about when we are conditioning on events as opposed to just general phrases. In addition to general event semantics like this, we also have to consider the individual instantiations of these events and the fact that phrases that are describing events can pertain to multiple different events that have taken place and may even be in your video corpus. For example, when people say the Notre Dame fire, they tend to be thinking about the April 2019 incident. The University of Notre Dame actually caught fire at one point too, and that's an entirely separate event that your model, upon given a query Notre Dame fire, has to differentiate between these two different existing events and try to identify which event the user is actually interested in retrieving. Furthermore, an additional complexity on top of the fact that we are switching modalities to primarily video and we're considering events, we then need to consider what it even means to be relevant to an event-based query. If you type in Notre Dame fire, you really want to be retrieving videos that look like this. But what about videos of the construction process after the fire? Those are partially relevant, but are they actually what we want to be retrieving from this model? What about videos just about the cathedral itself? These are all questions that we need to answer before we can put together a model that is going to be retrieving content based on the event data. So hopefully I've explained why this is a distinct and interesting task from traditional information retrieval and stuff that you see on the web now with platforms like YouTube. But that sort of presents a second issue of why do we actually care about this task? In the past 10 or 20 years, with the increasing ease of being able to take a video on your phone, a high quality video on your phone, and just immediately upload it to a website that can host that video online and present it to other people, we are entering a phenomenon of the modality of the information that we have as a society is shifting away from being primarily text-centric to being more video-centric, just in general, in terms of amount of data on the web. Back in 2019, so this is an old statistic, but back in 2019, 500 hours of videos were being uploaded to YouTube every single minute. And we're entering a phase of social media where a lot of the content is purely video focused as opposed to text centric. You have entire platforms where the primary form of information is in video. And so now we have a problem of we have this vast amount of information that is only contained within videos online, and we don't really have a good way to be able to sort through all of it, either for human uses or for downstream AI applications like RAG or something. For example, we could foresee a future in which we have a large collection of video data that doesn't have any text metadata associated with it, and we'd be able to output a human readable text document that describes the events that took place within those videos. And so now I'm going to briefly discuss some of the interesting design choices and challenges that are associated with this problem. In typical video understanding, the traditional paradigm is to just throw all of your modalities into a joint model that outputs a single dense vector representation for that video. But there are a lot of other methods to parse this video data that might be more useful in the context of video information retrieval. And so I'm going to go over first just the design choices and challenges associated with dealing with these individual modalities that you can extract from video. Of course, you have the visual content itself, the collection of frames that make up a video. You could go and pass all of these frames together into a large video understanding model. Or if you want, you could extract individual frames that best depict the key information presented in the video and create individual vector representations for each of them. In such a case, you'd have to consider not only how many frames are you extracting from the video, but also which frames to be selecting in order to maximize the information that is extracted and represented in your vectors. Similarly, you could actually just extract the natural language description of a video, in which case you run into a whole bunch of other interesting questions, mainly what sort of natural language descriptions are you wanting to extract? A picture's worth 1,000 words, and you could spend 1,000 words describing the color of the walls of this building in this image. But what you really want to be extracting is the spire falling in the background there. How do you get a model to extract that information specifically and put it into natural language that is helpful for a downstream information retrieval system? You run into a lot of interesting problems with audio content as well. Audio is first extracted, it's just a signal, but it can be extracted into speech data using ASR. This might not be in English. The majority of information on the web is not in English. You can either translate it into English, but then you run into the problem of you don't know if there's a full sentence that's actually being said in the video. It could just be half of a sentence cutting in the middle of a word. And you can also have the problem of there being other audio data in that video that isn't speech. You can have explosions, you can have music, you can have silence. How do these contribute to your overall, or the model's overall understanding of the video and help to retrieve the correct content? You have OCR, which is text content that is contained within the video itself. There's a large amount of rich visual contextual information that is paired with these individual text strings. And how do you represent that information? How do you identify what OCR content you want to be actually extracting from the image or video in order to pass it into a representation for retrieval? How do you translate it, especially in the case of when you extract the characters slightly incorrectly? And how do you go and synthesize all of that into a document or representation that is helpful? And then finally, there's the question of whether or not you're including the text description that may or may not come along with the video. We, in our task for scale, we create two separate versions of the benchmark, one of which we include the text descriptions of the video as potential input that can be modeled, and another version where it's not modeled. We do this in order to resemble the different kinds of tasks that you may encounter when you are performing video retrieval, whether it's over a corpus like YouTube where this sort of metadata is available, or a unlabeled video data set where you won't have this content at all. Once you're done considering the individual modalities, there are other questions to consider in your design of a model for this task. You have to identify whether or not you want to be individually constructing indices, or if you want to just create one joint index. If you are creating a joint index, you need to determine how you're going to consolidate all of the different vector representations for the different modalities into a single index. And then you also have to consider choices that need to be made during online retrieval after you've created these indices. For instance, the queries that a user might upload in natural language to retrieve videos might be helpful for audio or OCR content, but they might not be in the best format for good visual content retrieval. So when you are creating your indices for visual content, you might want to go and decompose the queries that users inputted into a format that would be more appropriate for individual video frames or something like that. And additionally, you have to decide whether or not you want to do re-ranking. So we can't consider the queries that are passed in to a video retrieval system when you're indexing the videos, just due to computational issues. But once you've actually indexed and retrieved a set of videos based on a query, you can then go and re-rank those videos using the query afterwards. But you have to consider the computational cost of doing this and what the relative performance gain is. You have to identify what the trade-off is there. And so these are just some of the questions that we were presented with and tried to answer during this workshop. It was a really unique scale. Typically, these scale workshops, they tend to involve one or two modalities. Last year, the topic was speech translation. But we were really lucky in that we were able to bring together a wide range of researchers from a wide range of expertises, ranging from video and visual understanding, OCR, natural language processing, ASR, speech information retrieval, and machine translation. And together, everybody worked to try to improve our retrieval system individually along each of these different modalities, but also together to create a final system. And so this was some of the members of the team who came together this summer for the 10-week workshop. And at this point, I will be passing it off to Reno to discuss the benchmark that we tackled during this workshop and the results.
Thanks, Kate. Right. Hello, everyone. As Kenton introduced and Kate introduced, I'm Reno. I was another one of the co-leads of this workshop, and I'll cover the task itself, how we set it up, and why previous data sets, because there are previous academic data sets, were not really sufficient, or we didn't consider them sufficient for this task, and then go on from there with the actual results. As you might suspect, with the growing amount of video content that Kate mentioned, there are academic data sets that are looking or that are trying to actually answer the question of can we retrieve videos. These data sets, however, are a bit smaller. They're I don't necessarily want to call them toy data sets, but they are much, much smaller in size, and they also focus primarily on English news broadcasts. So they're coming from very few sources. But as Kate mentioned, especially in the past few years and in the modern day, real news content is coming from anywhere in the world in any different language, in all sorts of formats, from thousands of different sources. So you can't really overfit on these small number of English news broadcasters. So real news content, basically we want to be able to retrieve both the professional ones, those are still valuable in some way, but also non-professional ones, so that when an event is actually happening, we don't have to wait for a news organization to curate the material and edit it down into something more digestible for us. We want to be able to also find the videos of events as they happen. So just to kind of give you a sense of the scale of things. So this is the primary standard academic data set, MSR-VTT. It's pretty small on here. You might suspect that I'm about to show you something much larger, and that is the case. So this is the comparison of what a standard text information retrieval data set looks like. And this is only one language of it. The entire data set is around 6 million documents that they're sorting through. And MSR-VTT is roughly 10,000, and that's split into train, development, and tests. So the actual test set is even smaller than 10,000. So this is good when you think about just how long in practice it takes to process videos. But when, as Kate mentioned, we're thinking about just how many hours of content are being uploaded to YouTube and TikTok and all other social media apps every minute, this is really not a sufficient task. Now, could we get to 6 million videos? That would be great, and we will probably hopefully get there eventually, just in terms of how much storage that takes. We didn't have enough storage to quite get up there, but we got to a point where we thought was a much more practical, or closer to a practical, like in the wild task. So to do this, we first wanted to find our kind of event-centric needles. To do this, this was a paper that Kate was first author on, and we submitted to NeurIPS last year. It was about 2,400 videos, about 260 events that are covering a variety of video types, so emergencies, political developments, elections, social events like festivals and sporting events, and scientific and technological discoveries. We found these events by looking at trending topics on Google and Twitter, and from several different languages or several different areas of the world. And most of these were collected in 2022 because we released this data set in 2023. We were creating the data set right before it, although it does extend back to 2015 and 2016. We could try to pull older videos or older events. Something that's more notable in video than text is that videos tend to get taken down very frequently, especially primary sources. So that's why we really pulled things that primarily for 2022, because those were the ones that were most likely to still have the primary like first-person POV videos still up about them. And overall, as I said, it's about 2,400 videos, 260 events. They're aligned with 468 documents. That includes a document in the original language, as well as a translated or an English version of that news article. These usually were Wikipedia articles when we could, because these were events that were trending on Twitter, so they'll likely have a Wikipedia page. But if they don't, especially in other languages, we tried to find an Arabic or a Chinese or a Korean article instead. And we used 5 different languages initially in this first version of Multivent. So as you might suspect, this does not solve the problem of being large enough to be a practically useful retrieval task. So we actually need to collect more distractor videos. So luckily for us, a few months before Scale, InternVid was released, which was a collection of around 10 million videos covering a large array of categories and a superset of the languages that we cared about. Not all of these were about specific events, so that not all of them had event-worthy content, but a decent amount of them did, especially in the news and politics domain. So what we did was we didn't take all 10 million, but we took around 108,000 from InternVid, split roughly evenly across the 5 languages that we cared about, plus a bit more of a new surprise language that we wanted to potentially introduce during Scale, and then a longer tail of videos that were marked as unknown language. So InternVid did not have, wasn't sure what language they were in. So the end result of the test collection that we had was 110,000 total videos. So for now that we have both the needles that we're looking for and also our larger haystack, we need to actually write the queries to find these videos within this haystack. The original Multivent paper kind of followed previous work where we just took the description from YouTube or the tweet associated with the video from Twitter and said, this is the natural language query that we're looking for. But we also, since we aligned these to text documents, we could try to make these in practice. When I am typing in something to YouTube or Google, I'm not typing out a full multi-sentence description of what I'm looking for. It's usually a few keywords, kind of like what Kate was showing before, where it's like Notre Dame fire in April 2019, and I hope to find videos based on that. So from the aligned text documents, we extracted around 255 base event queries. These were mostly Wikipedia titles. So just covering here, it's the 2023 restoration of relations between Saudi Arabia and Iran. That was taken more or less from the Wikipedia title. If we couldn't find a title, we kind of used content from the article to write our own. And then from there, we also had a second layer of query that's trying to target specific aspects of that event. So here, there are many things that happened within the restoration of relations between Saudi Arabia and Iran. One is the involvement of China. One was the reopening of the Saudi Arabian embassy in Iran, and then the actual agreement being signed, which was establishing diplomatic relations. So there were many different aspects that we tried to target here. And these were pulled from a set of annotations that we had done on the original Multivent corpus initially for information extraction purposes, but it was also useful for us for just query writing on targeted event queries. So what we wanted, one of the feedback that we got from our retrieval team during the planning of this workshop was that they were worried that this would turn into a classification task where you just kind of say, I want to identify multi-event videos and the difference between multi-event and InternVid, so that if I just build a classifier to throw out all the 100,000 distractors, we're back to the original problem. I'm not sure how big of a problem this actually was, because InternVid and multi-event do have some overlap in the topics that they're covering. But also to get around this, we wrote queries for specific event-based or videos that had event content in InternVid as well, and then mixed all the queries together so that you're trying to find both the multi-event needles as well as additional needles from InternVid as well. We didn't have the nice annotations that we did before, so we tried to follow more or less the path that we used for multi-event. We tried to write a base event query that was grounded in some kind of text document. So here the base event was the New York City rat infestation. We also asked annotators to write a query specifically using only the text description itself. And the goal was to still have it be about the original event, but to add one piece of new information that was not originally in the base query. So here they're hiring the director of rat control. We also did this for transcribed speech or for the speech itself, and then we transcribed it to assist our annotators. So here we looked at the rat infestation effects on the community, and then we did the same thing for OCR. So we pulled out all the OCR-able content. We also had annotators look at the videos themselves and then pull out text from there. And then we came up with queries that were answerable by the OCR. So if you notice here, we're not just taking string matching and saying, like, did you get director of rodent mitigation in your OCR system? If so, great, you solved the problem. We did want to add some kind of another general layer of understanding on top of this as well to make the task a little bit harder. So that's how we got to the overall test collection. We ended up with roughly 2,500 queries. You'll notice V2 because we started with V1, and as Kate pointed out, there was an infrastructure team that worked on this throughout the workshop, along with the other teams as they were working on their own specific ways to solve the problem. Basically, that team was developing the harder version of the collection or the harder version of the task. We kept the collections exactly the same so people wouldn't have to create new indexes, but we did about halfway through the workshop, we released new queries for them to work on. And then as well, we did not want people to hill climb too aggressively on our test set because there's always a concern of overfitting. We wanted people to run a lot of experiments, but we wanted to have a separate set for them to potentially do this without overfitting. So we created a second set. We pulled another 108,000 videos from InternVid only. And then we wrote around 1,400 queries for this one as well, that in the same way as we did for InternVid. There was no multi-event in the train corpus. So in that one, we provided the actual video IDs themselves so people could go and look at the videos online on YouTube to actually see what they're getting right and wrong. We did not provide that at test time. We anonymized all the videos, so all they had was actually the pixels themselves, and they couldn't go back and find the video descriptions. And so, as I mentioned, it often takes a very long time to process videos. So we wanted to avoid the problem where everyone was spending all of their time creating indexes and they didn't have time to try very many different things or different approaches. So we pulled out a subset of train that we called Train 2K. It was 2,000 videos, including all the videos that were relevant for the 1,300 videos or 1,300 queries that we had written. And this was basically so that it could quickly do model development, hyperparameter tuning, and figure out how many keyframes are useful and all the little details without actually having to run on the full 100,000 test collection, which often took a very long time. This is just a general language breakdown. So as I mentioned, we used the 5 languages for multi-event. We also, halfway through the workshop, we included a surprise language of Spanish. So that was the 6th language that we had collected some videos for. So it was pretty even across the board. As you can see, there's less queries for Spanish because we didn't have any in multi-event, but there's still around 200 queries. And then the video type, this is something that Kate and I have alluded to in passing, but in practice, this is a pretty key thing of like how hard is the video to find. So the professional videos are someone sitting at a desk or someone interviewing people on the street. There's a lot of text overlay, a lot of speech overlay, giving a lot of exposition saying, this is what's happening. This is the actual event that we're trying to find. So that provides a lot of extra auxiliary content or metadata that we can leverage to find these videos. When we talk about non-professional edited, it's similar to that, but instead of a professional news broadcaster, it's someone online kind of stitching clips together or maybe doing a voiceover over some text. It's still providing a lot of non-video content, but it's not created by a news broadcast organization. And then these final two were actually the ones that we really are most interested in. Those were when I take out my phone, I press record, and then I upload to YouTube. Now, in practice, we found, well, it's not that shocking to any of you, but in practice, we found that finding actual, like, true raw content with no speech or text overlay was very hard, and there's not much of that actually in InterVid at all. We're still working on collecting more of that. We did find a lot of that because we were targeting that explicitly in the original multi-event, so that's why we still have this true raw footage there, or the true raw category. However, especially now, there are many video editing tools that make it very easy to just kind of, before you upload, put a little bit of voiceover on it explaining what's happening, or especially put a text overlay saying this is what's happening, this is where the event is occurring. And all of that is very useful information for our OCR or text downstream text retrieval systems, but they're not always there, because if you just press play and upload to YouTube, all of that metadata kind of goes away. So we wanted to distinguish whether or not someone put text over or speech overlay on top of it versus if they just pressed upload. So where the final thing that we had to do is we had a initial set of relevance judgments, around 6,000, based on just the way we collected or wrote the queries and created the queries and collection. That was a good starting point, but as you can imagine, there are many, many other videos in this collection. We assume at this point that they're not relevant for any query, but in practice, since, as I said, the topics in InterVid and multi-event overlap a bit, and there's also multiple videos from different angles, or even similar videos that are uploaded that are near duplicates, it's likely that our distractor set has additional relevance videos in it, similar to a retrieval task. So we need to do a second round, or even a third round that we're working on now, but at least a second round of annotation to improve the accuracy of our of the task itself, and kind of make it more holistically robust. So we had the three topics, or the three categories that Kate mentioned at the beginning. So true relevant results were, in this example, we look at the actual videos depicting the fire itself. And then we also had, in the second round of annotation, we included any videos that we found that were partially relevant. So it's kind of it's either alluding to the event that's happening, it's possibly about the event. So it's, if you think about like the Olympics, basically a fencing event from Tokyo, if there's a fencing event, it's clearly the Olympics, but you don't know which Olympics it's from, that would be possibly relevant, because it could be from Rio, or it could be from this past year in Paris. Similarly, for partially relevant, that also incorporates things that are about the overall event, but they do not include all things that you're searching for with the specific queries. So like I mentioned, there were two levels of queries. One was just the base event. So one, can we see the Notre Dame fire? But then we also wanted to say, like, can we also find videos of the fire with the spire collapsing, or smoke coming out of the buildings? And so that if it was about the base event, but not covering all the things that we actually asked for in the query, we marked those as partially relevant. And then everything else was considered not relevant. So from this annotation process, again, given the time constraints and the multilinguality of this task, it was somewhat challenging, and we got to a decent amount. We had around 4,400 additional gold relevance judgments. We also added around 5,000 silver judgments. So if a video was determined to be very relevant for a base multi-event query, we assumed that it was at least partially relevant for the specific event queries, because we know it's about the event. It just may or may not have the actual additional content that we're looking for. So this was kind of to give models some credit for ones that we weren't able to annotate in time. And then using our best model, this is kind of the metric that retrieval experts have used to figure out how the coverage of the relevance judgments that they have. Ideally, you want to get to 100%. I mean, in a perfect world, you would annotate all queries times all videos, but that's obviously way too many for even a longer term task. So we would want to get closer to 100 here, and we went from around 16% annotated to close to 40%. All right, so that's how we set up the task, and we tried to make it harder and more meaningful so that any models that came out of scale were actually were more confident that they actually answered the problems that Kate laid out. So now I'll go through the evaluation. So before scale, the baseline that we had identified, or the primary baseline, was a system called multilingual CLIP. So CLIP is a image text multimodal model coming out of OpenAI. This is an open source version that's also in multiple languages. It basically does contrastive pre-training to try to put text embeddings and image embeddings into a similar space. And then you can either use the text classifier or the image encoder for whatever you want. For retrieval, you can use it so that you can pass the query through the text encoder. You can pass keyframes extracted from a video through the image encoder, and then compute the similarities here to get a ranking of all the videos. So I think this was a relatively strong baseline initially. I think it's competitive on MSR-VTT, although there are other multimodal models that have since shown to be a bit better on this, notably VAST and other things that Kate has worked on, and I'll touch on a little bit later. But at the beginning of scale and the lead up to scale, it was reasonably competitive on an English-only data set. On multivent, it actually was the best by a slight margin on the English version of the original multivent task, again, which is only 2,400 videos, so this is artificially easier. And then notably, all the other models that we had compared to, at least in our paper from last year, pretty much could not do any of the non-English retrieval at all. And multi-clip was the only one that retained its performance on our smaller test set. I will note that that's not a completely apples to apples comparison to what the task is now, because the queries that we had written, or the queries that we used for the original multivent, as I mentioned, were the text descriptions of the videos. So sometimes those were not in English. And now in our scale task, all of the queries are in English. So it's likely that this gap would be a little bit lower here, but still the multilingual aspects of multi-clip were pretty clearly improving in the tasks that we cared about. So we were reasonably confident in saying, leading up to scale, this was probably what we considered to be state-of-the-art on this task. So now I also wanted to introduce some baselines that only focused on specific modalities. So that for clip, we need to first select frames. And the way that people had done it leading up to scale was we selected 10 frames using a method from known as PyScene to text. It's basically trying to identify when the scene is changing during the video, and then putting kind of bounding boxes there, and then taking a frame from each of those segments. So for the primary vision-only baseline, we took the 10 frames from PyScene to text and passed them through the image encoder of clip, and then ranked the videos from there. For OCR, we again took the 10 frames from PyScene to text. We passed them through a open source architecture known as Paddle OCR, and they have lots of different models. We ended up choosing the English model because the other languages that they were actually pretty good at Chinese as well. So we used Chinese, but all the other languages were extremely poor, with over 50% character error rate. So it was effectively not doing anything. So at that point, so we made the decision that before scale, we would use primarily the English and Chinese as our baseline, and then we would pass it through the text encoder of clip. The other decision that we made prior to scale was that given the success, or given the strong performance of the multilingual clip, we were making the assumption that both the text encoder and the vision encoder of clip were equally usable, which not to give it away, but that's not the case. And then finally, for ASR, we used a standard, I'm sure many of you are aware of Whisper now, but it's a large multilingual speech to text model. out of OpenAI that's trained on roughly 680,000 hours of speech, and has shown to be very strong on especially this task of transcribing videos from YouTube, because a lot of the transcripts were actually from YouTube in their training data. And then we passed that through the clip text encoder as well for the ranking. And then before I get to the actual results, I just want to say what the primary metric that we used is. There are many other retrieval metrics that are interesting, specifically recall at 10 or mean reciprocal rank. NDCG is somewhat similar to mean reciprocal rank, but it's a bit more nuanced. So here, if we take these 5 examples here, where the first one was somewhat relevant, second was very relevant, 3 and 4 were not relevant, and 5 was somewhat relevant again. We first compute the discounted cumulative gain. So it's basically saying we used a 3-1-0 scoring system, where very relevant was scored as 3, somewhat relevant as 1, and not relevant as 0. And then basically this is, so we can see the numerators here are the graded relevance. The denominators are kind of rewarding early precision. So basically it's weighting higher the videos that are ranked at the top, and then progressively gets lower as you go down up to a certain point. So you could do the entire distribution. We did NDCG at 10. So even though there's 5 here, you can imagine a ... out to 10. And then it also incorporates recall, because it still does care that you get the one somewhere, at least in the top 10. And then you compare this to the ideal discounted cumulative gain, which says if you had a perfect ranking of this, so the very relevant one should be ranked first here, somewhat relevant should be after that, and then everything else should be not relevant. And then the normalized discounted cumulative gain, which is the metric that we're going with, is just DCG over IDCG. And this is on a 0 to 1 scale. There still needs to be, since this is, I mean, it's a pretty standard metric in the IR community, but I think it's not as well researched as something like Blue. And it's also very collection dependent. So I think with Blue, it's very easy, or it's easier to say kind of at a certain threshold, it becomes usable for keyword search. At a certain threshold, it becomes a decent system, and at a higher threshold, it becomes what you would generally consider a good system. Obviously, modulo all the problems that Blue has, but with DCG or NDCG, it's a little bit harder to say that exactly. From the IR community, it sounds like roughly 0.3 or so is on the border of being 0.3 to 0.4 is being on the border of a decent system, and then 0.7 would be getting close to a very strong system, 0.6 and 0.7. So this is where we started. The vision one here is just the clip baseline with 10 frames. Speech is whisper passed through the clip text encoder, and OCR is paddle passed through the clip text encoder as well. So there were many experiments that we ran through scale, and I will not cover even close to all of them, but I just wanted to kind of highlight 3 major insights here that resulted in a larger boost in performance. So when we can, we want to extract as much specific text as possible from any source that we can get. So from speech, from OCR, if we can get it from visual captioning, that's great. As Kate mentioned, often visual captioning is a bit vague and flowery language, which sounds very nice, but when you have 100,000 that are vague descriptions, it's not actually that useful for retrieval. And then once we have specific text that says these are just basically, especially anything that says specific entities or describing specific aspects of the event, then we can leverage all the decades of IR research to use their efficient retrieval systems. So the primary one that we used here, well, Colbert is kind of an umbrella term for lots of different models, but it's basically we leveraged a lot of the efficient high quality retrieval models developed from Scale 2021, which was on cross-lingual information retrieval. The second insight that we had was a lot of the text, even if it has useful specific information in it, it can be hard for standard NLP models to parse just because they're so noisy. So In ASR or speech recognition, that can be because there's not as much punctuation, or there's a lot of stuttering or disfluencies happening. In OCR, it's even worse because there's essentially no good way right now to put back together OCR in a coherent reading order. So they're kind of just seeing snippets or small phrases of text that are coming from anywhere in the frame, and there's not an easy way of putting them together. So one way that we looked that actually worked pretty well was we passed these raw outputs from ASR and OCR through a large language model like Llama to say, can you please summarize what's happening here? And even if that propagates some errors or hallucinations, it at least puts a lot of the specific content into a format that text models are more used to. So that results in a pretty strong boost in performance, especially with OCR. And then, as Kate kind of alluded to, when we combine all these modalities together via a late stage fusion, it does significantly better than any of the modalities did on their own. And I guess I also wanted to highlight, since large language models and vision language models are very, they're very widespread, they can do many, many things. And in fact, a lot of the best models or most recent state-of-the-art models on MSR-VTT are multimodal large vision language models. We spent a lot of time seeing if they could actually do as well on our task as they did on the smaller tasks. And in general, I think Kate can probably confirm the answer was no. I think I highlighted the LLMs here, or the summarization LLM with LLMs, as basically the one positive result we got out of large language models. I think they're very brittle, and we can go into that more. But yeah, it's basically, if anything, I was happy to note that large language models did not solve our task. All right, so final test results. Oops, I think, okay, I didn't put what these actually were, but the vision component here, we saw around a 23% improvement. We went from 10 frames from Piscine to text to 16 uniform frames. And then we passed that through a Siglet model, which is another vision encoder that out of all the vision models that we tried was the strongest one. We also, as Kate mentioned, we decomposed the queries to get additional boost in performance. With speech, we pretty much stayed with Whisper. Whisper is a very hard baseline to beat, especially since, as I mentioned, it's essentially trained on a lot of YouTube transcripts. So it's likely that it's even trained on some of our training data, although we don't have access to it. But passing that through Colbert and summarizing it, as well as translating it after, saw a pretty strong boost in performance, even though we're using the same initial transcripts. And then for OCR, we saw a huge boost in performance. This was not that shocking because it started out very, very low. And as I mentioned, Paddle was very bad on anything that was non-English content. And luckily, several of our co-leads had a very nice multilingual system that won a best paper at the OCR conference last year, ICTAR. And that kind of gave us a huge boost already. And then when we translated it and summarized on top of it, it just further boosts the performance. And then finally, when we combine everything together in a 6-way fusion between all the speech, just the speech and the OCR, and then we did a weighted fusion with the weighted re-ranking with the vision components, it resulted in an overall boost in performance of over 100% from what we considered to be a pretty strong baseline before scale. So I think this was pretty shocking results to me. I think if you told Kenton or I that we would see our performance double before scale, I think we would probably think you were crazy. I'm still looking at this, and I'm still obviously I know how we got to this result, but I'm still very, very pleasantly surprised by this. And then, as Kate mentioned, there's also another setting where if you have a human written description where it's saying this is what's happening in the video, and it's specifically written so that your video can be retrievable by a YouTube algorithm, we can do much better. And then the other thing I wanted to highlight, going back to the raw videos or the video types, raw videos were very, very hard. They were much harder than our overall task. as you can see, speech and OCR, which did very well on the overall task, there was very little useful information that we could gain from either of those. In vision, it did a bit better, but still was clearly a significantly harder task. And then fusing things together obviously doesn't help if you're fusing very bad ranking systems together. We did try smarter ways to rank things, and that will be continuing work. And then I'd also like to highlight that so this is just another example of when you have specific text, which is human written text about the events, those are still very, very useful. It is lower than the overall, but when you have the descriptions, we can still do a very good job of finding these raw videos. So as Kate mentioned, we brought in a lot of different researchers from many different fields, and it was very easy for us to imagine people just kind of going off and working on their own things and not coming back together until the very end. And we might not have a very coherent story to tell. So the way we tried to facilitate this was from day one, we had a leaderboard set up through something called Eval AI, where everyone could post their results and everyone else could see how they did. We also withheld all the judgments from the test set. So if you wanted to know how well you were doing on multi-event or anything in the test set, you had to post to Eval AI. So it was a nice forcing function here. I think also it kind of, once people got used to it, it definitely helped a lot. And I kind of just wanted to highlight kind of how we got from the 0.3 to above 0.6 and over 100% improvement using this leaderboard. And this also allows us to go back and say, this is where we were at this date, this is where we were at the next week, this is where we were at the next week, and we kept going. And also, since everything is multimodal, oftentimes people would see a good result on here from a specific modality and say, that's really great, I want to use that output. So that kind of just facilitated collaboration, especially once we got to fusing modalities and kind of combining modalities together. All right, so we're almost at time, so I'll kind of go through this very quickly. This is just a kind of nice line chart to kind of see where each modality started and where we finished. So at the beginning, vision was the best performing one, even better than the Oracle descriptions, because as we realized, using Clip's text encoder was very suboptimal. And also using paddle OCR for the OCR content was also clearly very suboptimal because it's significantly worse than the other modalities. So when we went to our award-winning multilingual OCR system from Dave Eder and Cameron Carpenter, who's one of the students here, I don't think he's not here today, but he's a PhD student, we doubled our performance right out of the gate, so that was great. And then the next insight that we looked at was a lot of different frame selection methods. How many frames can we use? What types of frames can we sample? And it turns out that 16 was roughly a good equilibrium for, well, it didn't improve any after on the vision side. It did continue improving on the OCR side because OCR is very noisy. So sometimes looking at up to 1 frame a second results in even better performance. For efficiency's sake, we kept it at 16 here. And the other thing was that we didn't have to do any kind of fancy scene detection boundaries, just uniform frames was sufficient. The other thing that we got from the vision team was initially we were pooling we were taking the mean frame for the rankings, and then we found, I'm sure there's many other ways that we can do frame representations or like top 3 frames, but the main insight that we had here was that just taking the maximum most similar frame was better than pooling all of them together. And then when we look at better encoders, specifically better text encoders, we saw large boosts in all the text performances once we stopped passing them through Clip and started passing them through Colbert models. And then we also, when we moved from SIGLIP, or when we moved from Clip to SIGLIP for vision, that saw an additional boost in performance. And then at that point, we started to merge the modalities together because we had we had reasonable systems across all the modalities. So now we were ready to start actually combining them in a meaningful way. We tried several different ways to do this. The way that is on here is known as merge high score. So basically, when we looked at the rankings of each video query pair, we just took the highest score across all three. And it's somewhat analogous to instead of making separate indexes for each modality, we just combine them all together, or like concatenate all the text together before we index. So the other way that we did was reciprocal rank, and that worked reasonably well. But merge high score was basically saying, does any modality think this video is relevant for the query? And then the other thing that we were seeing was, even though Colbert is ostensibly a multilingual model, it did better, or performed better, when we translated with a robust translation system. I didn't put it in here. We tried several different translation systems. In practice, the one that worked the best was Google Translate, which is not that satisfying to me. So I'm very much looking forward to Kenton's new work that's coming out soon, and we will immediately take it and use it. But basically, translation itself is challenging here because the text that's coming out of speech and OCR is so noisy that we really need, and also very short, especially in the case of OCR. So you really need a robust system that's trained on lots of 1 to 2 word pieces of text, rather than the standard way that machine translation systems do of full sentences. And then when we fuse these together, obviously we saw a large boost in performance on top of that. And then when we did a 6-way fusion of the translated and the original, surprisingly, it saw improvement on top of this. And then if you'll note, all the fusion work here was only text outputs. There was no vision components. And that was because initially, with just the naive way of ranking that we had, it did not help. So we tried a few different ways to do this, and there was a weighted fusion based on basically the newsiness factor of it. So this was kind of a takeaway from the difference in performances across the video types. So the vision components were most useful when the videos were considered raw footage, because there's really no useful content in the text that you could find. So basically, we tried to upweight the vision rankings in that case, and then downweight them when we had a lot of useful text to work with. And then the final feature improvements that we did, we incorporated the llama summarizations for OCR and ASR, and that saw a bit of improvement. And then we also did the query decomposition on the vision side. And then, as Kate mentioned, you can also, although it's expensive, at query time, you can take the top 1,000, say, results and then do a much more in-depth re-ranking using a larger, slower model like Mono T5, and you get you can kind of eke out a little bit better performance from there. So I guess I also just wanted to highlight, we had almost 1,000 submissions to our leaderboards across 21 people, including the week before our final readout. Our server broke and we lost, and I thought we had lost all of the submissions, and that was a bit stressful, but it was a good thing. It basically meant that everyone was using our servers so much that it was overwhelmed. So that was very nice. And this is just the final system diagram without re-ranking. This is just to show NDCG at 10 for this system. Again, is not using any of the Oracle human descriptions. The NDCG was 0.611, so that's where the or almost 100% improvement is. That how long it takes to create an index for all of these components, it took around 45 seconds per video. So if you think about this, and this is kind of hard to track because different things work on different GPUs, and some are much more powerful than others. But this was the approximate value that we came to. The biggest culprits here is Whisper is really, really slow. And we do have another system that I didn't highlight here, but it's almost as good, and it's several hundred times faster from Scale 2023. So if we were to actually do anything like this in practice, we would probably not use Whisper at this point because it takes a really long time. The other big culprit is using a language model to summarize. And then with re-ranking, basically the main thing that we're adding in is this big slow re-ranker at the end. The timing for indexing is the same, but just if you're willing to wait 5.5 minutes to get results back, you can get 2 points better on NDCG. So if you probably wouldn't be implementing that into Google anytime soon, but just in terms of a leaderboard, that's the thing that's at the top. All right, so I'm a bit over time, so I apologize for that. But just to go over briefly the takeaways, we established a new meaningful and realistic event-focused video retrieval task from scratch. No single modality was enough to solve this task. And the more specific text that you could get from any source, the better our text systems will do. LLM summarizations of the initial text outputs is very useful, especially for very noisy text. And then combining the multiple modalities is very helpful or works very well. Truly raw footage is still very hard to find, and which is I'm happy to see, even though we had very good results, there is a aspect of this problem that is very much unsolved. Not that the whole problem is solved, but especially the finding raw footage of events is very, very hard to find. So when I'm thinking about going into this further down the road, we plan to create another version of this data set where we focus more on these raw videos. And in theory, video captioning could be useful because basically everything I've said up to now is the more specific text that you can have, the better. But as I've alluded to, those tend to generate pretty vague text. So if we were able to do video captioning better in a way that was able to identify specific things that are happening and not just describing this color of the building or a man running down the street, then that would be very helpful for this downstream retrieval task. And then the next steps, we have lots of papers that are planning on coming out. The first priority is getting a paper on the task and then the overall scale paper. And we have lots of promising results that could turn into papers. I haven't touched on a lot of them, but there's a lot of people that have done a lot of good work. The data and task build for scale, we want that to increase community interest on this task. As Kate said, this is a very interesting problem and it's very challenging. So the first step for that was the goal is to have a shared task in the very near future. And then the other thing that we didn't mention, but I wanted to highlight was this wasn't initially our plan for when we started to think about the concept of scale. We really wanted to have a multimodal information extraction or content understanding scale. But as we worked further and further on this task, we realized that it doesn't really matter how well we understand the videos if we can't even find them. And so we wanted to see, can current systems actually retrieve videos in a larger in the wild setting than what we had? The answer was generally no, but when we fuse everything together and all the work that we did, now we can we're a bit more confident there. So once we will continue work on the retrieval side, but then another thrust that Kenton and Kate will definitely be focusing on is deeper content understanding tasks, saying like, now that we have these videos about these events, can we pull out specific pieces of information with the goal of eventually trying to do something like write a report about an event or a news article? And that's it. Okay.
You say that the summarization are there any what was the most surprising things that you thought LLMs or large models would have helped but correctly?
Maybe you could take that, Kate.
Yeah,
you have a lot of
yes. We had a lot of difficulty specifically working with multimodal large language models. We tried doing a lot of fusion work, trying to create a single dense vector from all of the modalities thrown into a joint model. We found that typically these models are trained on a very specific type of video language data, such that they perform pretty effectively on existing video benchmarks like MSR-VTT. But when you move towards more complex, semantically complex video data like we have in our scale task, the models sort of fall apart and fine-tuning isn't necessarily effective due to the architectures that these models have. And so we found that pretty surprising. And then a second area that we thought LLMs would, or VLMs would do better at is captioning for videos for different reasons. I mentioned this a little bit in the motivation, but the captioning of a semantically complex video is very difficult because there are so many different things that you could focus on. Getting a model to focus on the actual core event that's being depicted in a video is very difficult, and we failed to get models to do this successfully during the primary thrust of the workshop.
And I will add two more. We had a lot of thoughts on VLMs and LLMs. Especially there's new VLMs that are, in theory, can do OCR very well. So there's one called Florence that they say that they're essentially state-of-the-art on OCR. So that's obviously very appealing to us. So we did run a lot of experiments on Florence, and it was pretty decent on English again, and then terrible on the other languages. So I think they are probably working on a much more limited set of what they define as OCR. And then the other most surprising thing, I think, for me, was InternVid itself had, along with their data, they released a model, a vision language model, that was trained exactly on all the videos in our test set. So I think when we were looking at the infrastructure team building out tasks and finding other relevant videos, the natural assumption that we made was that we could use that model to find all the other relevant videos for specific queries. And we assumed that that model would clearly outperform anything that we'd ever seen in our non-cheating ones that hadn't been trained on our test set. In practice, that was not the case at all. And it did not solve the task, even in the small, like train 2K setting that we had. Because as Kate said, they were trained on captions. I believe they were generated in some way, but looking at yeah, they had their own generation system to generate captions about the videos, and just looking at those captions, they're really bad. I think people at our workshop, people even tried to train or fine tune on those, and it was just they're not. I mean, they're good for the task that they built, but it's not the same as the event, like specific event queries that we were looking for. So that was shocking, I guess, that like even training on the test collection is not necessarily good enough if you are not thinking about the queries or the natural language in the same way.